There are only 4 new equations left on the formula sheet, so I've broken this down into 2 narrated PowerPoints because the first 3 of the equations really all go together in the same problem. Here are the only 4 equations that are left, and you can see that 2 of them relate to velocity. You can also see that 2 of them relate to this thing called z. Z is something called the redshift. I'm sorry that I'm writing it in green. It's just the ink color that I picked up. Remember that a redshift means that something is moving away. The reason why we're using Z for the redshift is because, well, it's the last letter of the alphabet and everything is moving away from us, so it's going towards the end of the universe, you could say. So why don't we talk about blue shift in this part of the course? And that's because the universe is expanding. And the reason that we know that is because if we look at the spectra of galaxies, we see that they are redshifted. They're moving away. So we're going to be looking at the redshift. We're going to be looking at the velocity, how fast these galaxies are moving away from us. And we're going to use that to figure out the distance. So over here, you see that we now have wavelengths. This is going to be sort of a version of the Doppler formula, as we're going to explain in the next slide. So for a type of problem that we might do with galaxies, a typical problem would have 2 parts. The first, we have to calculate the velocity of the galaxy, how fast it's moving away from us. And we're going to do that from the redshift. Remember that the redshift is in red now. The redshift is z. And we calculate the amount of redshift from a version of the Doppler formula. So here, delta lambda, this is going to be the amount of shift. So this is going to be the shift of the wavelength. And lambda true is going to be, well, the true wavelength. Remember that whenever we had a Doppler formula problem, we had the true wavelength and the apparent wavelength. Now we're going to have the true wavelength, and we're going to have the total amount of shift, and we are going to divide them. Then we're going to take the redshift and multiply it by c, the speed of light, and that's going to give us how fast the galaxy is moving away from us. And then we're going to take the velocity, plug it into what's known as Hubble's law, and we're going to solve for the distance. Here is a typical problem. A galaxy's 21 centimeter line is shifted by 2 centimeters. What is the redshift? What is the recessional velocity? If h is 75 kilometers per second per megaparsec, what is the distance? So we're going to break this down into its 3 different parts here. So the first part says a galaxy's 21 centimeter line is shifted by 2 centimeters. So we have the true wavelength and we have the amount of shift. That's what we're going to plug in and solve for the redshift. So the redshift, I sort of always put a line through my z so they don't look like 2's. So the redshift is going to be equal to 2 centimeters, that's the shift, divided by the true wavelength, which is 21 centimeters. Now you can see that the centimeters are going to cancel, so the redshift has no units, what we call dimensionless. And so z in this case is going to be equal to, if you divide it out, 0.095. So that's the redshift. Now in order to get the recessional velocity, we have to take the redshift and multiply it by the speed of light. So the recessional velocity is going to be 0.095 times the speed of light. Remember, the speed of light is 300,000 kilometers per second. So if you grab your calculator We can multiply that out, and that comes out to 28,571-ish kilometers per second. So that galaxy is really hauling. So that gives us the first part of the problem. For the second part of the problem, we're going to have to use Hubble's law. Hubble's law is right here. Now, Hubble's law has three different pieces to it. We have the recessional velocity, which we just got. We have the Hubble constant, and the Hubble constant has to be given in the problem because different astronomers argue that h is this number or h is this number, so it's safest just to give it in the problem. And then the third part is the distance. Now, a word of warning about the units of the Hubble constant. The units of the Hubble constant are a little wonky. They are kilometers per second per megaparsec. And that's because h is sort of a unit conversion or a currency conversion back and forth between velocity and distance. So the kilometers per second, that refers to the recessional velocity. The recessional velocity is given in kilometers per second. The megaparsec refers to the distance. So the distance is going to be given in megaparsecs. And a megaparsec, 1 pc, equals 1,000,000 parsecs, or 10 to the 6th parsecs. We know what v is from what we just did. We're trying to solve for d. So before we plug some numbers in, let's try to rearrange this formula. So we have v equals h times d. We want to get d by itself. So we're going to divide both sides of the equation by h. If we divide both sides of the equation by h, the h cancels on this side, and so we simply have v over h equals d. So now let's go ahead and plug in the numbers. So from the last part of the problem, we had v was 28,571 kilometers per second. We're going to divide that by 75 kilometers per second per megaparsec. If you look at the units, you will see that the kilometers per second are going to cancel. So here we have 1 kilometer per second, another kilometer per second. If we grab our calculator and divide out those numbers, we end up with 381. Now, what are the units? The units are 1 over megaparsecs, right? Because we've canceled the kilometers per second with this kilometers per second, so it's 1 over megaparsec. That's like 1 over 2. 1 over 1/2 is just 2. 1 over megaparsecs is just megaparsecs. So our answer is going to be 381 megaparsecs, 381 million parsecs away. Better start walking and pack a snack.